So now we're going to move on to the last topic in chapter 3, where we're going to consider the differences between speed and velocity. So you should be on page 12 in your yellow packet. And up at the top, it says, recall the average speed is the total distance traveled divided by the total time of travel. And the difference to that is velocity is defined as the rate of change of position or displacement. So we pay attention to average velocity being the change of position divided by the time interval for that change. So in this instance, we have instead of VAV, this time we have it with a little arrow on the top of it, which indicates that it is a vector. So now it's the change in distance, which is actually displacement. So that has the vector and the change in time. So if you run around an oval track in 10 minutes with a perimeter of 350 meters and end where you began, what is your average speed in meters per second? So considering that you have a track and you're going to go all the way around it, and it's 350 meters in length, and it's going to take you 10 minutes to do that. Your speed is going to be the distance divided by time, and so you're going to have 350 meters divided by 10 minutes, and you're going to have to also include the fact that minutes, they want it in seconds, so that means you're going to also have to multiply 10 times 60. So you end up with 0.58 meters per second, and no direction is needed. So it ends up being 350 divided by 600. Average velocity, so what we care about is comparing your starting point and your ending point, and since in this case they're the same, your displacement is 0. So that means your average velocity is 0 because you have started and ended at the same location. Let's do another problem. So a cyclist takes 25.1 seconds to cover the displacement of 115 meters east from D1 to D2. So part A asks you to calculate the cyclist's average velocity. So for this one, they gave you the displacement of 115 meters east, and they told you it took 25.1 seconds to cover that. So we actually are going from D1 to D2, 115 meters east. We're going to take that divided by 25.1 seconds, and we should end up with 4.58 meters per second east. I suggest that you always check my math here, make certain that I haven't written down the wrong number or typoed something. And if I have, please let me know. So then part B asks us if the cyclist maintains the same average velocity for 1 hour, what is the total displacement? So we did calculate that this was 4.58 meters per second east, and 1 hour is 3,600 seconds. So if we know how to rearrange our equation, displacement equals time times the average velocity. So we get 3,600 seconds times 4.58 meters per second east, and we end up with 16.5 kilometers east. And again, displacement is a vector, so it needs a direction, so we need to carry that direction through our problem. And then in our last part, we really need to have a sketch drawn, which is why I had drawn this one earlier. So part C, if the cyclist turns around at D2 and then travels 565 meters west to the position D3 and it takes him 72.5 seconds, what is the average velocity for the entire motion? So if he started here at D1, goes 115 meters east, and then turns around and goes 565 meters west, what we care about for velocity is his overall displacement. So we need to compare D1 to D3, which means we're going to compare 565 minus 115 for his displacement. So in that case, we need to consider here the total amount of time it took him to do that displacement. So 565 minus 115 is 450 meters west. And it took him 25.1 seconds originally, and then an additional 72.5 seconds for the second part, when that totals up to be, that totals up to 97.6 seconds. So when we take that displacement divided by the time, we get 4.61 meters per second west. And again, velocity has direction. And we know that based on our little sketch, he ends up heading west overall by looking at our little sketch. So a couple more quick questions. Can the average speed ever equal the magnitude of the average velocity? If no, why not? And if yes, give an example. So what do you guys think? So yes, they can when the distance and the displacement are equal, and that's when we're typically in a straight line path. We haven't done any winding around. At that point in time, both the speed and the velocity will be the same, at least as far as their magnitude is concerned. The next one, a truck driver reacting quickly to an emergency applies the brakes. During the driver's 0.32 second reaction time, the truck maintains a constant velocity of 27 meters per second forward. What is the displacement of the truck during the time the driver takes to react? So we have an average velocity, we have a reaction time, so we need to rearrange our equation for velocity. Displacement over time to solve for displacement. So in this case, displacement equals velocity times time. So displacement equals 27 meters per second forward times 0.32 seconds. And we end up getting 8.6 meters, and it's forward, in the forward direction. So don't forget that displacement is a vector, so it needs a direction. So at this point, I would like you to work on pages 13 and 14 in your yellow packet. These are going to look very similar to what you've already did with distance and displacement, but this time it's on speed and velocity. And on the next video, I will go over the answers to those.